Hey there, math fans. Dr. Andy Lovelace here to make my first video in my series on math and nature. As I said before, I have a very long list of ideas, and I've lately been thinking that I would like to open this up to students. I'd like to make this playlist collaborative. So if you find something in nature that really interests you and you do a little bit of research and you're able to make a short, 3-minute video with some visuals about it, let me know and I'll add you as a collaborator and you can add it to this playlist. Wouldn't that be lovely? So I'd like to build this as math and nature that we all can share. This one's about ocean waves. I'm no expert on ocean waves. When I was at the beach this summer in Manzanita, which is at the Oregon coast, I took many videos of the ocean. This was a picture from one of them. And I noticed how the waves get really steep right before they crash. And here's a picture I found online. And here's after they crash, they seem to kind of go around like this. So I thought, well, that's not a sine wave. What is that? What do people know about? And I was like, there must be a lot known about this. So I started to dig around again and I found lots of papers, lots of articles, fluid dynamics. But my goal is to keep things simple, and I think we can. So I dug in a little bit, and I found this was from Hyperphysics website. So I did not make this image. I'll put the link in the description. But they have a little discussion of the wavelength of the wave, and they talk about various properties of the wave and how as it goes faster or in various conditions it might look more like this or more like this, and various properties about that angle, how at most that angle can be 120 degrees when it gets to this steep spot. So I was like, oh boy, there's a lot of math there. Where does this stem from? And what can I do about it? What can I say about it? So ultimately, this all comes from circular motion. That's something we cover, I think, in chapters 17 and 18 of our precalculus course. So what I liked was that, hey, I can talk about a lot of this just starting there. And from that alone, I could make visuals like you're seeing on the screen in the corner there. A few other resources. I used Wikipedia to get a few things. I found this online. Let's see, this was the World of Mathematics website about how the waves, how they dramatically decrease in intensity as you go further down, how it's related to the wavelength, how you can see that it gets more to this sharp peak as it gets closer to the shore. And some of this I had never thought of. And really my point in this is we don't have to be an expert. If somebody wanted to, they could do research on this. Many people do. But we need a little bit of math to just understand. Okay. So let me say a few particular things. So the main thing I've learned in my bit of researching was this. So if you look at the image on the right, the assumption, the observation is that particles don't move forward. And you actually can see this. I was at the beach the other day. I threw a stick in, and the stick pretty much stayed in the same spot for a long time. It didn't come in. It gradually moved a little bit. But the observation is out in the ocean. The wave is energy that passes through. The water's not actually moving that way. It's just going up and down at that point. And the particles on it have this behavior, this circular motion. So it's a model like that. So I want to say a few things about this and show you a few other visuals I've made. Okay. So it all starts with this circular motion idea. And it's a fairly simple thought. So let's assume that particles move in a circular fashion like this. Now, in reality, they might shift forward a little bit as they go, but let's do this idealized wave. And it's called the trochoidal wave. You can see I've never really even said that word. Okay, so let's look at this and say a few things about it. I'll move this over. And I'll get rid of this. Apologies. I'll make a shorter version. Okay, so imagine we have a particle here on the edge of this circle. Sorry, I made it smaller there on accident. And we're going to set it in motion. And we can do that. So I have some point on the edge. Let me move it back here to here and start rotating it. So if you take Math 120, you'll find out how we study that. It comes from that unit circle. And really it all comes from this r cosine of theta, r sine of theta. So in Math 120, you'll study this. You'll learn the unit circle. Something traveling at a constant speed, you'll have this. Now we refine it a little bit. So in this case, I'm going to have the r be the height of the wave. So let's call it h. And the angle we typically break down as follows. Whatever the starting angle is, plus however much we change the angle. So the amount we change the angle, we typically write as omega t. And again, I'm doing this as a motivation for these basic tools. Okay. Omega is typically how many radians or degrees, let's say per second, that you rotate. It's called your angular speed. Typically, if we want it to go, so in my picture I have it going clockwise because I wanted the wave to look like it was going to the right. It's negative if it's clockwise, positive if it's counterclockwise. So I picked a couple just random numbers. I decided for simplicity of this discussion to have it start at the right. So the initial angle is 0. So I took this to be 0. And I just made this a small number, so it took a little while to go around. Otherwise, it would have been spinning like mad. Okay, so this was my model. So there we go. So I put in a couple numbers. I think the numbers I have in there right now, the height is like 0.6. The omega is like 0.05. So it's a pretty small number. And I've got it. Oh, and I made it, because it's going clockwise, I made it negative. So this was negative. These are the sorts of things you would talk about. So if you want to study circular motion, Math 120 is a course where you would do that. All right, so then what did I do? So then I said I would like to graph a lot of these, but I would like to shift over the center. So then we go like this. Here's x. Let's make this an A. Let's make this a B. So that would shift it over a little bit. I think for my example, I made B 0. So let's just keep that 0. And that was my model. Lastly, so I did that. And I actually plotted a bunch of these. And I spaced them out. So I'm having it plot a bunch of these moving points. It's amazing how much that does look like the top of a wave. So equally spaced out, a little bit of an adjustment in the angle, you get this picture. So you have a whole bunch of particles. This is just a bunch of little specks on top of the ocean rotating around. And then I used the fact that by the time you get, to a certain level, it doesn't weigh very much, and I added a few more. There's something wrong with my bottommost one. What did I do? Oh, I added something in because I was editing. There we go. There's our wave. That's just coming from circular motion. A lot of circular motion, but it's just coming from circular motion. Okay. So then the next question is, what if we just wanted to model the top of that wave? So let's go to time 0. Boom. The next question for me was this. I don't know what the natural next question is. I don't study this. So the next question is, what is the top of that wave? It's not a sine wave. Let's get rid of our other things so we can just look at it. What if we connected those dots? Maybe I'll throw in a few more dots. No, let's just leave it. Oh, we can throw in a few more. Here's 80 dots. Oh, I didn't see any difference. Okay, so what we can do is we can move the center of the circle. So I'm going to take the center of that circle and slowly move it to the right. How do I do that? Well, I'm going to replace this by something that's changing. If I wanted to move at some sort of constant speed to the right, I could write this. Now, I decided to make things as simple as possible and just make it so that the speed at which it moves to the right is the same as the angular speed. That doesn't really make sense, and I just wanted to keep some of the solving and working easier, but you'd call that V however fast you want to do it. So there's a T here. Let's see what happens. So I did that. I made that omega T, and then I plotted that polar curve. So it's still just circular motion, but also I'm making the center of the circle change. Okay, I did that here. At this point. And here we go. Ooh, that was fun. That's called a trochoidal wave. It's like a spot on a circle that's rotating. And you can read more about it. Just search for ocean waves, trochoidal waves, and you'll see this parametric equation. My goal here was to explain that parametric equation. It's really circular motion. You can see it sitting here. And this is the observable fact that we see. And this is where the center is changing. So that's at a particular moment. It doesn't make as cool of a visual as having all the particles, because that looks more like the ocean, the original one I was showing you. But I wanted to show you the top of that wave. So there you go. Okay, so that's it. Now you could study the top of a wave. Now some interesting things happen here if we look at that peak. So I'm going to draw a little line at that peak just so we can talk about it and say a few things about it. And you should know, if you took calculus, you could find what the slope is there. You could find various properties about it. But let's just look at that peak. Okay, so what happens if the wave gets higher? If everything else is kept the same, but the wave gets higher. I'm going to adjust that a little bit. Ooh, it gets steeper. It's steeper, steeper, and it eventually comes to a point. Ocean waves can look like that. They look like that right before they crash. And it turns out, based off of the wavelength, that can have a bigger or smaller angle, but it's been proven that it can't really go past 120 degrees. I thought of trying to do that in this video, but I decided not to. It's taking too long. This is already too long. What happens if you go past that in a trochoidal wave? Well, let's take a look. Here's what happens, is it starts to bend back on itself. And that's what happens if you just rotate the circle. It does this. So my question was, is that really what the trough of a wave looks like? And so I took a picture of one. And a cool thing about Desmos is you can throw it in here. I added a few parameters so that I could tweak the circle. And I got the following. So I had to tweak a little bit, but that looked pretty darn good as a model. So it really is circular motion in a way. I found that to be an interesting exercise. So let me know what you think. Check out trochoidal waves. Hopefully the next time you look at the ocean, you can think about that a little bit. I found that to be a fun little diversion. All right. Let me know what you think.